Okay, this lesson here, 6-3, exponential growth and decay, can be easy, but it really depends on how you interpret things and how you read word problems. If you can't read the word problem, this will be extremely, extremely difficult, okay? Notice this. Cindy's buying a new car, okay? When you buy a new car, the car value depreciates, okay? So if it depreciates, we can call that exponential decay because it's going down. If it's growth, it's gonna go up, okay? Important. In order for us to find out an exponential growth or decay, we have to find our percentage, okay? Usually when it's decay, the percentage is lower than 100%. So we're always dealing with 100%, okay? If it's less than 100%, then it's decaying. If it's more than 100%, it's growing, essentially, okay? So let's look at this example here. The population of Hillville grows at an annual rate of 15%. What's the estimated population in 5 years? Well, we're adding 1 because it's going up, and the percentage is 15. We need to convert 15 as a decimal, by the way. So when I add 0.15 to 1, there's your annual growth rate starting from 5,000. Once we find our function, that becomes 5. We then find our answer. Just plug it in, voila, you got your answer, which is in this page right here. Boom, okay? Let's look at this one here. This right here, actually, it's increasing by 1,000. It's not increasing by a percentage, okay? This is gonna be linear, okay? Because it's not a percentage. If it's not a percentage, it's gonna be a linear growth, not an exponential growth, okay? Keep that in mind, okay? 1 plus R, that's growth. Okay, 1 minus R, that's decay. Important, very important. Oakley dokley. Okay, compound interest. Let's talk about money, okay? It's actually pretty much the same thing as growth and decay, but now we're doing it so many times per year, okay? So many times per year. So when we talk about interest rates and then we're compounding at a certain time, notice that number there. The number is quarterly. And when we think of quarters, we think of 4 because 4 quarters make $1, okay? Know this function here. What you start off with, your percentage over the number of times the number over to the power of the number of times how many years, okay? It looks complicated, but let's look at an example here, okay? Kimberly's family invested a certificate of deposit, a CD is what they call it, okay? The interest is compounded quarterly. So we have to label everything, okay? So this is your P, this is your R, this is your N. This is gonna be your T. R is a percentage as a decimal is 0.08. Quarterly, that's 4. Bing, bang, boom, plug them in, boom, bam, bing, and then you get your answer, okay? Now, what if it's done annually instead of quarterly? Well, annually means 1 because there's only 1 year in a year. So just change N to 1, boom. You actually get less money if you're compounding it annually compared to quarterly, okay? However, what about semi-annually? Well, when you see semi-annually, that's 2, okay? Monthly, that's 12. Let's do the semi-annually one first, okay? Okay, so I don't want to find the difference between the two. Let's just set it up. And then we'll go from there, okay? So in this case, semi-annually, okay, that 1 changes to a 2, that 0.08 and everything else stays the same. Okay, here we go. So it's gonna be 3,000 times 1 plus 0.08 over 2 to the power of 2 multiplied by 15. And the really cool thing about this is we can use good old Desmos to type it. The way you see it is the way you type it in. Okay, so here we go, 3,000, okay, 1 plus 0.08 divided by 2, okay, all of that risen to the 2 times 15, voila, 9730.19, okay, it's not difficult, 9730.19, voila, okay, not difficult at all. Here we go, almost done, okay? A video is labeled a fan favorite if it receives at least 1,000 views per day, okay? Amelia posts a video that got 8,192 views on the first day, and then it decreased 25% every day. And how many days will it stop being a fan favorite? So we need to figure out when it's going to be less than 1,000. So this is decay. It's 1 minus R. So that means it's 1 minus 0.25, which means it's 0.75 starting with 8192. Boom. We then graph it to figure out when it's going to be less than 1,000. And it looks like it's between 7 and 8 days because it alternates from over 1,000 to under 1,000. Okay? So now let's look at this. So instead of 25%, let's talk about 20%, okay? This as a, whoa. This is a decimal, is 0.2, okay? So it's gonna be 8192 times 1 minus 0.2 to the power of x. That is your y. Let's now graph that to figure out when it's gonna be less than 1,000. And it's gonna be a lot slower, okay? 8192, 1 minus 0.2, oops, power of x. Boom. Let's find the table. Okay. Boom, bam, boom. That's not going to work. Boom, bam, beam, bam, boom, bam, beam. Got to keep going. Boom. Between days 9 and 10. Okay. Between 9 and 10. That's not what I wanted to do there. Between 9 and 10. Okay. Voila. Yeah, got it. Okay. Not difficult at all. One more example. Okay. Making comparisons, okay? Notice how the peak of population, you're starting with 144 and you're decreasing 8% each year. All you got to do by finding rate of change, again, you're finding the slope, okay? You find the slope between, let's say the comparison between 1 and 5 and 6 and 10. Find the inches of the two, find the slope, and you make your comparisons, okay? This one has a smaller rate of change than this, meaning that this has a better rate of change, okay? Because it's going downward essentially, okay? So because it's going down, it's decreasing essentially, okay? So now notice this, okay? If I'm, let me go here. How would the average rate of change over the same intervals be affected if it increased, okay? The graph instead is gonna do this, whoop. So that means the 6 through 10 is actually gonna increase more than the 1 through 5 because notice how here it's smaller, right here it's bigger. Okay, very important. Last one, okay? Rich is comparing the cost of maintaining his car with the depreciating value, okay? You're starting at 20,000 bucks and it decreases by 15%. The maintenance cost is 500 bucks and it increases by 28%. So we need to graph those two functions. When do they intersect is when they're both gonna be the same. So at what year? And it looks like around year 9, both the cost of the car and the cost to repair it are going to be exactly the same. Okay, so for this try it question, explain how to use tables or a graphing calculator. Graph your functions. If you have more than one function, find out where they intersect. And notice how in this example, did find where they intersect to see when both values, both spending in this case, and how much the car is worth are exactly the same. So obviously, notice this. After year 10, for example, notice how the cost of the car is actually less than how much it is to repair it. So whenever there's a car accident, okay, this is a little food for thought. Whenever there's a car accident, let's say your mom or dad crashes their car, okay, and the repairs are $5,000, but the car is only worth $3,000. The car is totaled, meaning that the repairman's not going to fix the car because the car now is worth less than how much it is going to cost to fix the car, meaning if they're going to get $3,000 back, we're going to use that to buy a new car. Yay. All right, that'll do it here. Definitely read all this, obviously. It's self-explanatory. Have fun. 6-4.